Hello again, my dear students. Now this is part number 4 with our rectangular waveguide lecture. If you remember, I told you in the beginning of this lecture, and also I told you in the part number 3 that in this part number 4, we will be fully dedicated to the representation, the plotting of the electrical fields, the surface fields. Herein, we are going to use some online tools in addition to our handwriting plotting in order to understand how electrical fields and magnetic fields and electrical and surface current behave inside a rectangular waveguide. We are going also to use some, maybe I will going to upload to you some previously implemented console file that also can demonstrate the same field. However, during this lecture, I will just demonstrate these fields using an homemade, maybe, or our university-made simulation tool, online simulation tool that is accessible by everyone using the internet. You can access even using your mobile phone or your tablet. So let's now start our lecture. Okay, so first we are going to flash back the main output we have reached by the end of lecture number 3 or part number 3 in this lecture. So if you remember, my dear students, we have investigated deeply what's called the TE10 mode. And actually we chose this TE10 mode basically because this TE10 mode is the fundamental mode in our rectangular waveguide. If you remember here, when we choose the TE10 mode, this is actually because A is normally greater than B, so the term 1 over A is smaller than the term 1 over B. That's why the first cutoff frequency will occur at the 10. Okay, and then we have investigated the component of the A10 mode. I think here we have got it. Yes, this is the cutoff. Yeah. Now we can substitute with m equal 1 and n equal 0, which is the TE10 mode. And then we get the components of the TE10 mode. You have to remember that Ez is equals to 0 from the beginning because this is a TE mode where the electrical field longitudinal component is equal to 0. So we have only Hz, and by substituting in this equation, also we get another 2 zeros here in Ex and Hy, I think. So Ex, yes, and Hy are also equals to 0. So by the end of the day, you have only 3 components, Hz, Ey, and Ex. During this lecture, we are going to investigate deeply how we can plot such an electrical field. Of course, you can implement the same using any other mode. So you can just apply the same theory, the same approach in any other mode, either a TE or a TM mode. This is typically the same. I just choose the TE for 2 reasons actually. The first is that the TE is the most famous mode. This is the fundamental mode. And the second is that it's somehow easy for mathematical reading to do because we have only 3 electrical and magnetic field components instead of 6. We have another 3 with zeros. That's why life is somehow easy in dealing. That's why I choose the TE0, so the TE10 mode. However, as I mentioned, you can typically apply the same approach on any other mode. So after that, we calculate, of course, the phase velocity, we calculate the wavelengths, and also we calculate the power, if you remember, using the relations that the power is the real part of the E cross H complex conjugate with this half, indicating the square of 1 over root 2 due to the root mean square values, where we indicate here the power P10, we call it the P10 power because simply this is the propagating power for the 10 mode. And this is also, there is also a very important point here when your power is a function in real beta. So whenever beta is imaginary, I mean with beta or with a frequency smaller than the cutoff frequencies as beta will turn to be imaginary, then the power will tend to be 0, no power will propagate. So power will only propagate if the cutoff frequency is greater, if the frequency is greater than the cutoff frequency. Then we turn to the sources of losses, and I told you that we have 2 sources of losses. Either the dielectrical losses, which is the losses inside the dielectrical material, or the conductor losses, which is the surface current or the surface losses due to the conductor. We investigate deeply the losses, the power losses due to the conductor. Here, this is the term we will be used. This is J square over 2. Again, 2 is just the root 2 square. So root 2 due to the root mean square value. And this is the surface resistance, or what we call the sheet resistance of the cover. So now what we have done in part number 3 is that we calculate this JS, or the current, and we calculate this JS knowing the fact that N cross H will get our JS. So N cross H at x equals 0, and cross H at x equal A, and the same as at y equals 0 and at y equal B. So you have a full surface current. You can easily calculate these full surface currents using the above equations, and then we calculate the overall surface current in the four sheets, or the four surfaces of the four faces of the rectangular wave. And finally, we say that again the power losses is equal to our S integration for the JS square, and then we calculate the total power losses. That's why here you can see that that 2 disappears. This is simply because you have inner faces and outer faces. So after calculating the power losses, you multiply by 2, so you can include the inner faces and the outer faces losses. And finally, we calculate here alpha C, or we call it C here because this is the conductor losses. So alpha C, or the conducting attenuation coefficient, is simply the power loss in the phase, which is PL over 2, over the overall power losses, over the overall power propagating, which is P10. So by dividing PL over or PL over 2, sorry, over P10, you can get this alpha C2. So this is simply what we have done, and we also plot this. Okay, so let's now turn. This is just a flashback. You can find more details about that in our part number 1, part number 2, and especially part number 3. Now we turn to the plotting phase, or let's start to investigate the tool. What we have. What is the tool? So this tool is it can be easily found over the e-learning page, and also I will also include it in the comment area associated to this YouTube video, so you can just access it either using the YouTube video or using the e-learning page as you like. So now here, let's do it. So this is our tool. This is our solve tool. What you are going to do is very simple. Let me show you our laser pointer. Okay, so just you can check the electromagnetic hub, and then you go to what's called the rectangular waveguide tool here, as you can see. So now this is it. In the tool, we have actually 4 tabs indicating 4 different functions. Let's start investigating each one, and during the investigation, I will reflect how this tool should help you in solving problems and in getting experience with in-class tasks and the final exam problems. Because basically, from the first impression, you will told me that it's just an inline tool for demonstration. How can I use it for studying? So this is actually very, very important, and maybe by the end of this video, you can understand that by using this tool very well, you can investigate a lot about your depth of understanding to the module as well as your experience with solving problems. Okay, so the first one is a very important one, and actually this is somehow associated to an example I solved. Sorry, I solved it with you in this slide. Okay, sorry. In this slide, as you can see, this is a very simple example. It has given A and B, which is the dimension for rectangular waveguide, and he told you please calculate the first 5 rectangular waveguide moves. So the first 5 cutoff frequencies. So very basically, without any effort, this is directly the equation we already have concluded for the cutoff frequency. You already know that the first mode of course, is the 1, 0 mode. So it's very simple. You can just substitute here by 1 and here by 0, which will end with, I think we already have this equation. Yes, this one. So this equation is 1 over 2a root mu epsilon. And please remember that whenever you are considering air as your electrical material, then 1 over root mu epsilon is simply c, the speed of light. So this is simply c over 2a. So what you are going to do in solving this problem is that you are going to say, okay, I have a, which is 1.07 centimeter. Then very simple, let's do it in this manner. Okay, so I believe that now you can see my simple whiteboard. Okay, so what you are going to do is very simple. You will say that, okay, let me stop the screen. So you will say that I have A equals 1.17 centimeter. Let's write B for our knowledge. So B equals 0.43 centimeter. So as you can see, life is easy here. So what you are going to calculate first is you calculate the F cutoff for the 1, 0 mode, which is simply C over 2A. So it's 3 times 10 power 8 over 2 times 1.07. And don't forget 10 power negative 2, which is the conversion to meter. So by doing this, simply you can get the cutoff frequency. It will be something like 9.7. I think, yeah, 9.1. Okay, so 9.72 centimeter. Sorry, not centimeter. 9.72 gigahertz. Okay. This is perfect, and I think you can do it in your final exam or maybe in your in-class test very easy. Doesn't need more effort. But what if I told you that I need to calculate the next mode? Okay, so you will go to the equation, the general equation, the general cutoff equation. So FC NNM is equals to, let's do it, 1 over 2 pi root mu epsilon. Again, this mu epsilon can be easily replaced by C. So 1 over mu epsilon is C. Root m pi over A whole square plus n pi over B whole square. This is very simple. So you have A and B. You can substitute. But the question is, what is the next mode? What is the question? I mean, what is the value of NM? For the fundamental mode, you are sure that M equal 1 and N equals 0 is the fundamental, is the first cutoff mode. But what is the next mode? So here you have actually 3 probabilities. The first probability is that the next mode is the 2, 0 mode. So you increase M by 1, and the M still is equals to 0. Or the next mode is the 1, 1 mode. You have M equal 1 and N equal 1. And the third mode is 0, 1 mode. So you set or you return back M to 0 and you increase M to 1. So what you are going to do in your final exam is simply to calculate these 3 modes. No other way. You cannot expect which is the next one. So what you are going to do simply is you will calculate these 3 modes. If you calculate these 3 modes, my dear student, you will get here 19.44 gigahertz. And in the 0, 1, you will get 24, this right here, 24.19 gigahertz. And in the 1, 1, you will get 26.07 gigahertz. So this is the only way, my dear. Just calculating the three, and then, okay, the minimum one is here. So this is the second cutoff. And then this is the third cutoff, and this is the fourth cutoff. As you can see. So this tree is the only way where you can investigate the order of units. Now you are searching for the second mode, so you have to make it like that. Usually, we are interested in the second mode. Of course, the first mode is a very important mode, but the second cutoff is also very important. Why? Because in our rectangular waveguide, my dear student, we are defining what's called the band of the waveguide. What is the band of the waveguide? So, for example, in these examples, you call it a K-band waveguide. Maybe in some examples, or maybe in your final exam, or in class test example, I told you that this is a 5 gigahertz band rectangular waveguide, or a 10 gigahertz rectangular waveguide. What is the 10 gigahertz of 5 gig? Actually, it is a range of frequency. Again, it's a range of frequency at which the rectangular waveguide is operating in its single mode. Again, it's range of frequency at which the rectangular waveguide is operating in its single mode. So now, if I told you, please calculate the band, the single mode band for this rectangular waveguide, the answer is simply to substitute the second cutoff with respect to the first cutoff. Because now, if your operating frequency is 10 gigahertz, so by checking this table, you will say, okay, if I'm operating at 10 gigahertz, then I only have one mode, which is a TE10 mode. If your operating frequency is 15 gigahertz, again, you're still operating with a single mode. But what if your operating frequency is 20 gigahertz? Then another mode will start to appear, which is the TE20 mode, and then no longer a single mode rectangular waveguide. So herein, it is roughly 10 gigahertz, maybe slightly less than 10 gigahertz, is the band where your rectangular waveguide is operating in a single mode. Okay, so how we can use the tool in this? If you return to this equation, my dear student, you can find that the main factors that affecting the sequence of the mode is the values of A and B. You know that A is smaller than the is greater than, but based on the ratio between A and B, the sequence of modes will change. So let's make it try. Let's go to the example here. Here, this first tab, which is the tab we are now discussing, is investigating simply the sequence of the mode and the cutoff frequency. So this is typically the same table you just showed in my presentation slide. So here you have two ways to deal with it. Either to deal with a standard rectangular waveguide, so this is just a drop-down menu here, so you can deal with any standard waveguide, or you can go to a customized waveguide. Herein, this is, for example, our example. So we have here A and B. A, and I'm sorry, so I will take here epsilon r is equal to 1 to make it air. And then I will change A to fit with the one in my example. So I think here epsilon r is A in 1, I think so. There's no information about the epsilon r, so epsilon r is 1. So now A is 1.07 centimeter, which is 10.7 millimeter. So simply, I'm going here to write 10.7. Okay, and I need also to write to find B over A, which is a ratio between B over A. So the ratio between B over A, let's do it here with the calculator. So it's 0.43 over 1.8. It's 0.43 divided 1.07. Then the result is nearly 0.4. So this is a ratio between B over A. So I will go now to the tool again, and I will charge here to make it nearly 0.4. Okay, so that's 0.4. So now you can see here the results. Okay, so now I'm I did a mistake here for this example. Epsilon r is equals to 2, not 1. I'm sorry for that. So this is epsilon r is equals to 2 now. So I just insert epsilon r is equals to 2 to get the same results I had in my presentation. So I just modified to include that epsilon r is equals to 2. So now epsilon r is equals to 2, and this ratio is roughly 0.4. So as you can see, now your first mode is a TE10 mode with 9.92, which is nearly the same here. 9.72 here, 9.92. Actually, this is actually because the ratio here is somehow approximated. The ratio here is not typically 0.4. So maybe I try to shift it to something like that. So, okay, so as you can see, this veil starts to somehow get more and more closer for higher modes. So this is for epsilon r number 2, epsilon r equal to, sorry, and then this is the values here. So this is the first mode, which is the 1, 0 mode. Then the second mode is the 2, 0 mode, as you can see. And then the third mode is the 0, 1 mode. And finally, the fourth mode is the 1, 1 mode, as you can see here. So, and so on. Now, of course, you can calculate this using the equations again, and you already, I believe you already understand this tree format. So you can calculate it here or there. This is not a problem. But let's start to examine the effect of A and B. For example, what if we decrease the ratio? When we decrease the ratio, that means that B starts to be more and more smaller with respect to A. So please check. So now, please check. Now, your first mode is TE10. Your second mode is TE20, but your third mode is TE30. So the sequence of the modes starts to change with respect to the A to B ratio. Let's go one more. Again. So as you can see, somehow it saturates. But what if we go to this side, for example? Now, please check here. Now, for our larger values of B, TE01 becomes the second mode, TE11 becomes the third mode, and TE20 becomes the fourth mode. Of course, as you can see, the fundamental frequency is independent on B, because simply it depends only on A. It will change if I change A, which I will do after this step. But now for this example, the second cutoff frequency sequence change with the change in the ratio A, B to A. So very simple. If you here you have TE01 and then TE11. Let's go, for example, to this case. Oh, yeah, now the sequence change. Again, TE01 is the second, but TE20 becomes the third, and TE11 becomes the fourth. So you can adjust the sequence of your modes based on the ratio between B and A, which is the main actually concept I'm trying to deliver in this example. To know that the sequence of your modes is controllable through the ratio B over A. Now, if I return back to my 0.4, which is the starting value, and I'm going now to increase the A, for example, to be 12. So as you can see, now the fundamental frequency starts to increase. Or now, sorry, it starts to decrease here, for example, because actually the fundamental frequency is inversely proportional to A. So whenever you increase A, the fundamental frequency will decrease and vice versa. So for example, if we go for A equals 8, for example, you will have now the fundamental frequency increase. So to control the fundamental frequency, you are dealing with A. To control the sequence and the band, you are dealing with both A and B. Now the band is roughly maybe 12.5 gigahertz. The band between the first frequency and the second frequency. So if we return it back to it was 10.7, I think. Here, as you can see, the band has been affected somehow. And also the sequence, or the frequency, of course, of the second mode have been affected. So now this is what we call the rectangular waveguide design parameter. You can design the parameter, which is A and B. You can choose your parameters, A and B, with respect to the band and the range of frequency you are interested in. So I'm dealing with 7 gigahertz, 10 gigahertz, 8 gigahertz, 11, 12, 16, whatever it is, I can adjust the parameter with respect to this band. So this is the first important note I would like you to know. The second one we already did in our previous lecture, which is calculating the main parameter. As you can see, the main parameters are the cutoff frequency, the propagation coefficient, and the wavelength. This is lambda g, as you can see, because this is simply that guided wavelength, which is 2 beta equals 2 pi over lambda g. So simply lambda g is 2 pi over beta. And I think we already calculated this. Here we can control, of course, as you know, beta is a frequency dependent parameter. So let's check the equation one more time. So yes, it's perfect. Okay, so this is beta. This is beta for the TE10, for example. And as you can see, beta is function in k, and k is function in frequency. So that's why beta is a frequency dependent function. Beta is a frequency dependent function. That's why in our slides here, you have to insert the frequency at which you are considering, because this beta will change by changing the frequency. And also you have to consider, is it air or another dielectrical, so you can change the epsilon r, so you can play with that. And also you can use either standard waveguides or a customized waveguide, so you can just change the outside. I believe this is somehow easy. We already make it a method for TE10 in our example. You can just substitute with any frequency, and then you can get the parameter you need now, as you can see in the equation. So this is a simple equation, k square, which is, if it's air, so it's k naught square, omega square mu epsilon. So if you have the frequency, you have k, and and the a is given, which is 10.7, for example, in our example. So you can calculate any beta for any frequency. And of course, simply by using 2 pi over lambda, you can calculate, or 2 pi over beta, so you can calculate lambda g also in a very simple manner. So this is somehow now let's turn to the third and important issue, which is plotting the electrical and magnetic field components. This is our next step, my dear students. Okay, so let's start doing this. Now, if I would like to plot the electrical and magnetic field, then I have to study in which plan I'm interested in plotting the electrical and magnetic field. So in doing such a plotting, you have to select your plan. Of course, usually it makes sense to use a cross-sectional plan. So just to cut your waveguide, and then this is your cross-sectional plan, which is the XY plan. Whenever you are plotting your graph in the XY plan, then you are considering only the X and Y component. You are not considering the Z component simply because this Z component is perpendicular to the plan you are plotting along. So you are just considering the X and Y component. So in this example, I told you, for example, I am interested in plotting the X and Y, or a cross-sectional, XY cross-sectional, assuming that that is the direction of propagation, of course. And I'm interested in plotting the XY position, XY cross-sectional for the ELH. Now, that's why I choose the TE10. It's a very simple way to be plotted. So now you can make it very easy. How? You can make it very easy because you already have EX equals 0 and HY is equal 0. So you only have one component. You only have one component per electrical and magnetic field. So what we are doing now is just we are going to start to plot such a component. For example, let's start with the electrical field, which is E1. So let's start now to plot this electrical field. Okay, so let me for a while stop sharing my screen and write with you the equation for the electrical and the magnetic field. So now I'm plotting a cross-sectional area. So let me remind you here. So if this is, so this is Z, direction of propagation. Then we have our rectangular waveguide. We have a rectangular waveguide here. What I'm doing just is that I'm cutting a cross-sectional area of this rectangular waveguide. So this is the area. And I'm going to plot the components. Generally, we have 4 components here. EX, EY, HX, and HY. Sorry, Y. This is one. That's right. So, as we are in a TE10 mode, so we found that EX is equal to 0 and HY is equal to 0. So simply, what we have as an electrical and magnetic field component in the XY plane is simply EY and HX. So let's start with the electrical field. Let's start with EY. The expression we already have reached in our lecture. So I'll just copy it. So we have minus J omega mu by over KC squared A A10. Then we have sine by over A X, and finally we have E power minus J meters. Okay, so this is the E component we have. How we are going to plot such an E component? First, you have to distinguish your parameters. That's why I'm using different colors in writing this equation. Here we have three different portions of this equation. We have constants with respect, when I say constants, it is a constant with respect to spatial parameter. It's constant with respect to x, y, and z. Of course, this omega is a frequency, so it's a frequency-dependent function, but with respect to space, it's a constant. What I'm going to plot now, my dear students, is an XY plot. What I'm going to do is that it's just an XY plot. So for this XY plot, the function is this red part of the equation is constant. Okay, so just this red equation, I can call it E node E or anything like that. So I will skip all this and write it, for example, E node Y. So just a constant of the refractive index with respect to space again. Okay, then I have part of the function, which is in blue now, is function x, and another part of the function, which is in green, is function z. But, and there is actually a very important something I'm missing in this equation, which is the direction. This EY is a vector, so we have AY here. Okay, but here you are plotting a cross-sectional in the XY plane. A cross-sectional in the XY plane, that means simply that z is constant. Whenever you are in an XY plane, you have a constant value of z. So as far as this is the constant value of z, then this green function turns to be a constant also, because there is no z variation in the arc. Z will vary only if we are considering here this plan, for example, the y-z plan. So this is a z variation. However, if we are considering only the xy plan, then this is not that there is no z variation, and then this green curve is, or this green portion of the equation will turn to be constant. So what you are plotting simply is a sinusoidal signal, very easy like that. It's just a sinusoidal signal. Okay, so how can we plot such a sinusoidal signal? Here we have x and y. We don't have any variation. We don't have any variation here. So for any constant value of y, I mean, for example, constant value of y means, for example, something like that. Or something like that. These dotted lines are constant value of y. For any one of these dotted lines, you should have identically the same value everywhere. You should have identically the same value everywhere. Because this equation is not a one dependent. But please don't forget, my dear students, that this is a factor in the right direction. We will consider it later. No. Now, what about this sinusoidal signal? What about this sinusoidal signal? So this sinusoidal signal is, as any sinusoidal is, has an alternating positive and negative. Generally, the negative value is the starting value because the equation is a negative. So for x equals 0, sine 0 is equal to 0. So I should expect a 0 value here. Whenever x is equals to 1, for example, then now the equation starts to appear. So then now the equation starts to have some values. This value most probably will be in negative because sine is a positive, negative, and tan positive will be positive. Till you reach the value x equal a. At the value x equal a, the function should return back to 0 because a times a will be cancelled with a, and then sine y is equal to 0, and then you have 0. So this is your first value. Till you reach the value 2a, then you have the second 0. Okay, what will happen in between? What will happen in between is that you will have a sinusoidal signal in the y direction. So you will have something like that. And so on, as you can see. So these fluctuations, I'm plotting these arrows in the y and negative y simply because this function is in the y direction. So that's why I'm plotting this function in the y and in the negative y direction. And this is simply the plotting of our function. Okay, so can we repeat the same process on the H component? Of course, yes. Let's now repeat the same process on or using the H component. Okay, so before going into the H mode, let's start to see this E mode on our tube. So let me please share the screen. And let's go to our mode. So this is the same adjustment. I go now to the fourth tab, which is the field plot. I adjust A to be 10.7 millimeter. Epsilon R is 2. Operating frequency, for example, 10 hertz. So that's why I have only one mode, because if you remember, our atom was at 9 and the next atom was at 19. So when the frequency is 10 gigahertz, you have only a single mode. I adjust again the ratio B over A to be 1.4. Of course, this is not so important now because we only have one mode, so it doesn't matter. And now this is the TE10 mode. I choose to plot the EX and EY. Now we don't have EX, we only have EY. This is clearly appear in the graph. As you can see, all arrows is directed onto downward in the Y negative Y portion. It's a negative because we already include negatives in the equation. If you can see in my band now in the top right corner of the screen. So this is a negative. And this scale actually, I believe this is in centimeter. So at x equals 0, you have 0. And at x equal a, which is 1.07 roughly, you already have 0. So this is the 2 zeros you already have in your graph. So and between you have the negative cycle of the sinusoidal. If we continue furthermore for x greater than 0, you will have, here you can see my top right corner screen, you will have the other pole to pole. This is simply here. This is the region from 0 to x equal a. Now you can make another from a to and so on. Of course, we are only interested in this region, which is the dimension of your waveguide, because this is actually somehow hypothetical. This is outside the dimension of your waveguide. So you are only interested in this region, which is the dimension of your waveguide from x to y. And I think this is in centimeter. As you can see, that's why at x equal 1, which is a 1.47, you have this the next zero value. So this is very simple how you can plot the electrical field. So let's do the same exercise using the magnetic field. Okay. So now for the magnetic field, let me first copy paste the equation of the magnetic field. Here. Okay, so H, now we have Hx. So let's write the equation. Hx equal. H is equal J beta y over Kc square A times A10 sine y over ax. I'm sorry, I forgot to make coloring, but you can make it in another way. E power minus j. Again, similarly, the same exercise. We are just repeating the same exercise to make sure that you understand the concept well. So, similarly, the same exercise. Now we have three portions of the equation. This is the first portion. Again, it's independent on the spatial component. It's independent on x, y, and z. So we can consider it E, sorry, H, x naught, for example, any value. And then this component is again constant because you are considering an xy plane. So in the xy plane, z is equal to constant. So this is again a constant. What you have only is this sinusoidal function, sine by x over a. But don't forget, now you have a x component. This magnetic field is the x component. So now we are going to plot xy cross sectional. And in this xy cross sectional, you have all your arrows directed to the x direction over negative x direction. And you have a variation with x. You have a variation with x. So for any constant value of y, there is no variation. For any constant value of y, there is no variation. This is very important. So again, you are doing the same experiment. You will say, okay, at any line of this way, or any line of this way, any line at any line of this, you have a constant value. So what you are going to do is you are plotting this sinusoid. Again, at x equals 0, the sine will tends to have 0. At x equal a, the sine tends to have another 0. In between, you will have this increasing and then decreasing function. So as you can see, the increasing and the decreasing of the function is simply determined through the length of this arrow. So this arrow length can easily indicate the length, the arrow length can easily indicate the magnitude. So this is the maximum because simply you are plotting a sinusoid. So this is the maximum value here. And on the corners you have minimum, then you have 0, 0. So this is x equals 0, and this is x equal. So this is your function. So now you can plot the magnetic field in this manner. Again, let me now return back to our tool. Again, I am adjusting the same parameters, and now I'm plotting only the magnetic field here we have only hx, hy is equal to 0. That's why all arrows is directed to the right. It's directed to the right because it's positive ax. If it's a negative ax, it will be directed to the left. And this is a field we just plot in our paper, as you can see. Of course, now you can see the mix, which is hx and ey. You can say it in a mixed manner. These blue curves indicating the electrical field, and this is the red curve indicating the magnetic field, as you can see at the combination of this. Now, the final stage of this lecture is, what about the surface current? We are interested in plotting the surface current of our rectangular waveguide. Of course, we have 4 surface currents at x equals 0, at x equal a, at y equals 0, at y equal. I will going to plot one of them, and then you can repeat the other 3 using the same manner. Of course, again, let me repeat it. We are doing this for TE10 mode. However, you can repeat the same with the TE11. Okay, so let's do the exercise now, and let's plot the electrical, the surface current of our example. Okay, my dear students, now it's time to return back to the surface current. Okay, to do so, let me return back to my presentation slides, please. And let's go to the slide where we have determined the surface current. Here is the slide. If you remember, we defined that we have 4 surfaces. On each of them, we have a surface current. And this surface current is given as a J equal A cross H. So this is a relation we use surface current. Here is the 3 examples at x equals 0, at x equal A, and at y equals 0. Of course, you can automatically do the first one, which is at y equal B. Now let's do the example at x equals 0. So if you remember, it was very easy. We multiply the surface, the unit, the vector representing the area, which is now in the x direction, cross with the h component, which should be in the z, because here you have 2 h components. You have an x, you have hx and hz, but ax across ax equal to 0. So you will have ax across hz, and ax across hz will give -1. So we have negative a10 e power minus j. This is simply the j at x equals 0. Now we are interested to plot such a current on the surface x equals 0. The surface x equals 0, my dear students, is a yz plane. So our coming plot will be in the yz plane because we choose that x is 0. So what we are going to do is as follows. Now we have our function. Let's first start to write our function. Our function jx at x equals 0 equals negative a10 e power minus j beta z in the ay direction. Now we would like to understand the concept of this function. So in this equation, my dear student, you have a negative sign, a constant, and a function of z, and all this in the ay direction. So you have not to think about the constant. It's just a constant. Here now, you couldn't ignore the z. In the field component, we ignore the z and we say z is equal to constant, because simply this is our xyz plane, this is our waveguide. While we are plotting the electrical field or magnetic field, we consider the xy plane. So in the xy plane, z is equal to constant. Now, in this field plot, we are considering the left face. Oh, sorry, this is the left face. Yeah, we are considering here the left face at which x is equal to 0. So now we are considering that y z plane, this plane, the y z plane. So in this plane, z is value does not constant. So simply what we are going to plot is e power minus j beta z. What we are going to plot is e power minus j beta z. So how we are going to plot e power minus j? We have to search for, again, whenever you start to plot anything, you have to consider what is the constant, what is the variable, and also you have to consider at which values your function will tend to be. Now, for any value of z, you have a constant function. So whenever z is constant, then you have a constant function. Whenever z starts to change, then you have a variation in z. So for any line like that, you have a constant function, because this is a wide range, and in this wide range you don't have any function. However, your function will change in the z, so your function will make changes here. Okay. So how your function will, so what you are going to do is just to plot one signal in this, right? And then you are going to repeat it upward and downward, because across this blue line the function is static. Function is not binding. All your arrows will be in AY or negative AY. So either to the downward or to the up. Okay. So what we are going to do is as follows. What we are going simply to do is that we are going to express where this function is constant and where is this function, where is this function is maximum and where this function is minimum. So if we investigate this exponential, e power j x, negative j x doesn't matter. Then actually it doesn't matter because it's an even function. So e power j x and e power minus j x are the same. So e power minus j x will be maximum if this x is equals to any multiple of y and y, and will be minimum if x is equals to n y over 2. So to investigate it more, let's return to the fact that beta is equals to pi over lambda j. So your function is e power minus j 2 pi over lambda j times z. So for z is equal 0, for example, you have a maximum, which is e power minus j 0. So this is a maximum. So here, in this case, you will have a maximum. This maximum will be directed into the negative ay because simply your ay in your magnitude has a negative sign. So this function will be directly directed into the ay direction. So whenever you have this function, let's do it. You will have function like that. It's a maximum function directed downward because we have a negative sign here, and this is a maximum. Again, what is the next maximum? The next maximum when lambda is when z is equals to that's when z is equals to lambda g, for example. When z is equals to lambda g, then we have another maximum, which is 2 pi. So here at lambda g, if you assume that this is lambda g, then you have another maximum. Okay, then where is your third maximum? You have another maximum when lambda g, when z equals lambda g over 2. When z equals lambda g over 2, you will have e power minus j pi, which will give you something like that. So you have here a maximum, and a minimum. The minimum will turn with a negative to a positive sign. Where is your zeros? Your zeros is, for example, when z equal lambda over 4. If z equal lambda over 4, then this will be e power minus j pi over 2. So here, this is 0. This is lambda over 2. This is lambda. And here, this is lambda over 4, for example. So here you have 0. And for 3 lambda over 4, again, you have 0. So this is your zeros. So here you have 0. In between, you have a exponential decaying form. I'm sorry, this is in this direction. And then it will turn here. So it reaches the maximum and so on. So we have zeros, sorry, we have maximum at 0 and lambda, because 0 returns to e power j 0, lambda returns to e power j 2 pi. This is the 2 maximum. And then we have minimum at lambda over 2, and we have zeros at lambda over 4 and 3 lambda. Let me make it in a clear way. So, if this is the z-axis, and this is the y-axis, I will plot a cosine function here to illustrate the case. Of course, my plotting is not so good, so it's not as symmetric, but it should be symmetric. So here, as you can see, we have e power minus j 2 pi over lambda z. If z is equal to 0, this is here. If z is equal to pi, this is here. If z is equals to lambda over 2, so you have a pi, then this is here. Of course, all these lambdas are lambda sheets by the way. Okay? Then, if z equals to lambda over 4 or 3 lambda over 4, so we have 0. So let's reflect this here. Okay, so we will say. Now, if it's 0, this is maximum, but the function has a negative value, so it is directed to the negative A1. So this is directed to the negative. And then, similarly here, this is directed to the negative. And then this is here. This is now negative, so we need a negative to that A1. In between, we have zeros here. We have zeros here. So in between, we will have something like that. And so we have this sinusoidal variation in the circle. And now you can plot your surface current in a perfect way. Of course, this shape will be repeated upward and downward because you have no variation with the y-axis. It's only a variation with the z-axis, not a variation on, or there is no variation with the x-axis. This is very important. This is, my dear students, is one of our very, 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 very important examples actually dealing with the plotting of the surface current. So what we are going to do now is that we're going to show this on our presentation here. So as you can see, this is typically what we did. This is lambda over 4. This is 3 lambda over 4. This is lambda over 2. This is 0, and this is lambda, as we typically did together in our plot. Simply, of course, I'm using here the same parameter. I can also turn now. Of course, again, this is not so important because our operating frequency is 10 gigahertz, so we only have 1 minute. But now you can, for example, go to the upper surface and make a similar curve, or you can go to the left, the down surface, or the right or the left. You can make whatever plot you want, and you can measure everything you need here based on this. So I encourage you, my dear students, to go through the other three fields. We did this one. We did this x equals 0 js, which is the left-hand side surface. Now, my dear students, you can go to more and more examples, either by considering the other two faces or by considering other modes. So, for example, in this example, I encourage you to plot the TE11 mode. So you can simply go to our general equation. Here is our general equation. But instead of substituting with m equal 1 and n equal 0, you will substitute with m equal 1 and n equal 1. And then you will get the that 5 component for the TE11 mode. And then you can plot the current, you can plot the electrical field component, the magnetic field component, and also you can also plot the, calculate first actually the surface current using the same equations, and also calculate the total, and also we calculate the total surface current in the four faces of your rectangular waveguide structure, depending on your structure or depending on your electrical transverse electromagnetic TE010, TE01, or whatever it is. So this is generally all the type of plot that you can do with such a very interesting tool. I encourage you, my dear students, to go deeply with this tool, because it can be a very good way where you can understand different fields of plot. You can check actually your solution by easily going into the tool and plotting in the paper, like what we have done now. I just start by plotting on the paper and then go to the tool to check that my plotting is correct and so on. So you can repeat it n time with different modes and different equations. Now, this is actually the termination of this simple guest lecture related to the rectangular waveguide, microwave circuit systems, and communication systems. So thank you very much for being with us for these 4 parts of the lecture. Hope that we satisfy your needs and we satisfy your expectation regarding your understanding to the rectangular waveguide. And hope that you can reflect your understanding in our rectangular waveguide to other types of waveguides, maybe parallel plates, circular, cylindrical, and coaxial cables as well. So thank you very much, and maybe see you in another course. Thank you.